Welcome to the Windshield Chronicles, a mental sequence of operation. This episode brought to you by our good friends at HVACRedu.net, workforce development online for the HVACR industry. Learn more at HVACRedu.net. All right, welcome everyone. Thank you all for joining, and we're hanging out today with our good friend Todd Kler. Todd, how's it going?
Howdy.
All right, so everyone, two HVAC and automotive nerds walk into a bar, right? So, well, how can it go wrong from here, Todd?
I don't know.
All right, well, welcome everyone. We'll get back to the actual intelligent side of this thing, but we're going to have some fun. You know, we're here to have fun, but we're also here to talk about transitions that's happening in our industry and to help ease a lot of the discomfort that is out there, especially when it comes to new technologies. So for those of you who don't know, Todd and I, we got a little bit of age to us as technicians, right? We've been around for a little while, but both of us have also been part of the automotive industry. We've both worked on vehicles. As technicians, I'm sure a lot of you are the same way. So we have learned to embrace change with the things that we work on. Now, as technicians, a lot of us are very mechanical, right? That's why we do what we do. But it doesn't always just stay there. How many of us started by building bicycles when we were young, right? And then worked on our own vehicles when we got to that point. So I used to flip vehicles. Even in high school, I used to flip vehicles, which means I had to learn how to work on them, right? So when we start talking about the evolution of the automotive industry, there are some very significant things that have happened in automotive that are almost identical to what we're seeing in our current transition in the industry. So today we're going to spend some time talking about evolution of two separate industries and how they are kind of merging now, finally at this point. What is our first tools? Were they plastic? No, most of the time it was things that we pinched fingers with and broke stuff with. Yeah, we've talked about, scavenging through, spare stuff for parts for things to tear apart and try to fix, and that was just kind of part of it. So let's look at what happened with automotive so we can see where we are right now. And hang in here, because we're going to show you some things that are going to help inverters make a lot of sense, because a lot of people are afraid of inverters, and we really need to be aware that inverters are the new standard. It is. We spent time almost a year ago with David Brennan from Rheem looking at the new lineup of equipment and realized that, man, almost everything was gone that had a contactor, except for the hybrid systems that had an inverter board plus a contactor that ran on inverter up to about 75 to 80% and then switched over to contactor to run full 100%. So it took the inverter board out, so it wasn't using any excess wattage. I've already talked to some of our friends over at Johnson Controls going, hey, yeah, we're really heavy on inverters. And Daikin is saying that they're here to inverterize the world. That's the mission of Daikin, right? So let's look at vehicles real quick, and let's look at some of our lineage, right? We've seen some big transitions in the 1970s, and that was really based on fuel efficiency, the demand for fuel efficiency, because the cost of fuel was ridiculous. Energy to run those engines, right? So we're really just talking about that internal combustion engine, the cost of the fuel to run it.
Yeah, and some of our audience may be too young to know, but back in the 70s, the fuel shortage. There was odds and evens of your license plate to get fuel.
Yeah, it wasn't like you can just go down to the gas station like we can now. You waited in line to pay premiums like we pay now for fuel. So we took the internal combustion engine, and this is the important part as an analogy in our classrooms, and especially when we're talking with our technicians and students. When we started evolving our internal combustion engine, it wasn't about reinventing the internal combustion engine. It was about making it more efficient, right? So we started working with emissions quite a bit. That's when we started utilizing catalytic converters, and that's when we started making our vehicles lighter. We had an increase, and then we leveled out through the 80s, right? We're still talking about carburetors. We're still talking about mechanical ignition systems. We're still talking about big, heavy boats, right? There were some pretty heavy vehicles in the 80s.
Steel.
Lots and lots and lots of steel. So once we got into the 90s, we started looking for other opportunities to change the fuel efficiency of that internal combustion engine, right? So how did we do that? Well, we're going to dive into that. We're going to show you some of the things that we did and how similar it is to what we're doing in HVAC. So let's look at HVAC, right? HVAC industry, just looking at SEER in cooling and heating capabilities, we've increased a little bit over time, but relatively stagnant. If we look at the increases, like in automotive, we're talking 3 times efficiency changes in many applications. We haven't went that far in HVAC.
Not yet.
No, but we have started trending upward. Well, we're getting ready to make a big trend upward, but we need to understand how we do that. So let's take a look at where we went from and what we went to in automotive, and we'll show you those analogies in HVAC, right? So let's think about these vehicles of the early 80s, early 90s when we started making that transition. We were talking about internal combustion engines. We're talking about pistons that were being driven by connecting rods, being rotated by a crankshaft, ignited by fuel, ignited by spark and air, and relatively crude controls. You know, we still had points ignition systems in the late 80s, and we were using chain-driven timing systems.
And it was reciprocating.
Look at,
our good friend Ty did a great video yesterday on one of his medias, and that, hey, the reciprocating compressor is dead. That's because it's not going to come back.
It's not. It's phasing out. We're looking into more efficient designs.
All that clearance space every time it comes up, that piston comes up and down.
It's right. It's wear. So we looked at better ways to lubricate. We were looking at that internal combustion engine. We're going to pick on like some small block Chevy, small block Ford stuff, just for analogies, so that you can see what we did. We didn't completely re-engineer the internal combustion engine. We changed a few things to make it more efficient. We added fuel injection. So we took off the manual carburation and we put on digital fuel injection. We put on electronic ignition so that we could control the advance of the spark, so that we could fine tune that ignition so that we had the best fuel efficiency, whether we were in the torque power band, the high RPM power bands, where we were cruising. We could modify the ignition electronically. And later we went to variable valve timing.
Yeah.
So we removed those mechanical components, all right?
And went digital.
We went digital. Now, Todd,
Yep.
What did we do with the internal of the engine?
It's the same. I mean, it's still the same today. It's all reciprocating.
It's still a reciprocating block. It's still got a crankshaft with connecting rods and pistons, and it's still made out of a lot of the same materials. Even.
I mean, I use the analogy, for those of us who remember the old Mazda RX-7s, they had rotary engines. It's very similar to the rotary technology compressors that we have.
Same
now.
Design. Exactly. And you know what?
Similar.
Man, I wish we would talk about this beforehand. I'd thrown some rotary in there. Because it was about efficiency. So, Mazda came out that rotary engine, you put it in the RX-7s real early because it was a very efficient, high RPM engine. We got a lot more RPMs in our rotaries today, don't we? All right.
But they were fuel hogs.
They weren't the best. A lot of those were still carbureted too. We started getting into some fuel injection, but more throttle body and not multi-port. All right. So let's talk about our hogs. Let's talk
electrical hogs. That is.
Let's talk about our electrical hogs that have been around, and think about this. There are still some reciprocating compressors out there. Not a ton, but there are some of them. If we think about the efficiency of our single stage and 2-stage equipment, we're not getting too high. Maybe topping out in the 16 SEER.
18 if you're lucky.
Depending
on the matchup. Depending on the
matchup and airflows, you might be able to get up there, but that's like really pushing it to be able to get to 18, right? So if we look at what our traditional, and I'm going to call these traditional or legacy air conditioning systems, we're talking about a lot of fixed orifices. And I just had this conversation last week. Paul Grimm, I don't know if you're out there, buddy. If you are, hop in here and chime in on this. I had a good friend of mine from a major distributor call and said, hey, we're worried about some of our dealers because they're throwing a fit about this new SEER 2. And they said they're going to change brands because they can get piston matchups at some other brands. I said, well, go ahead. They've got it left for probably a few more months, and then they're going to be back to ground zero, because they got some old stock they're trying to get rid of. Yeah. So fixed orifices is what most of us grew up with. I mean, tons of fixed
cap tube on a lot of things.
Cap tubes on stuff. Absolutely. So we had fixed orifice, contactor-driven, single-speed operation systems. So we had motors that ran at single speeds. Yeah, we'd have different speed selections, but they ran at one
speed,
desired speed.
One tap.
One tap. And we had compressors that run on single speed, single RPMs, even if it was a 2-stage. So if you're not real comfortable with a 2-stage system, all we're doing is bypassing some of our discharge gas back into the suction so that we reduce our compression ratio, which in return just does what with our capacity?
Goes down, but your fidget seater is only that much, but you got hot gas coming right back.
Yeah.
And it's even more efficient, but not that much.
Not tremendously.
Nah.
Yeah. So what we are doing is industry is evolving, and this is not just in residential air conditioning, light commercial air conditioning. I mean, this is in refrigeration as well. We're starting to see a lot of inverters. In residential refrigeration, a lot of our refrigerators are already inverter, if you didn't know that. A lot of our window air conditioners, especially ones that are going with things like R32, a lot of those are going inverter already. So what is inverter? Well, that's what we're here to dive into to help you understand that all inverters really run the same. It's just a change of the controls on our internal compression engine. Isn't that what we're talking about? The vapor pump? We're talking about an internal compression engine. So how do we make it more efficient? We take out our piston. We start utilizing things like thermostatic expansion valves and particularly electronic expansion valves, which I love. Mm-hmm. We're going to use control boards, and we're going to use variable speed motors in our fans and in our compressor.
But how do you speed up or slow down a compressor or a motor?
Right. Where's that magic?
You can't just adjust the voltage, right? Because what happens? Well, for all of us who know Ohm's law,
about that. Let's do it Ohm's law.
Go for it.
You go on display.
Make the math easy. 100
volts. All right. Hold on. All right.
100 volts, 10 amps.
Okay.
What do you got for watts? 1,000, right?
That's right.
Okay. Let's get rid of the drop the voltage in half and go 50 volts. What happens to your amperage? 20. Because the wattage is the wattage, right?
Exactly. All right. So we can't fluctuate the voltage. So how are we going to do this? How are we going to modulate a variable speed motor? Remember, we're talking a variable speed motor in our air circulation and in our vapor circulation, right?
And a lot of us might know that already. And I know I saw some refrigeration techs that I've worked with that chimed in already, and they've been doing it in refrigeration and commercial industrial refrigeration for years. VSDs and VFDs, right?
Variable frequencies. We're not changing voltage.
We're going to change the frequency. And here in North America, we use 60 hertz, 60 hertz. Well, if you wanted half speed, 30 hertz. But how do we change the frequency? You do it with a drive or an inverter.
All right. So let's look at components. So we have a very thorough understanding of the change in components. Because those of you that are used to working on conventional or traditional systems, you know what components you have. You're comfortable with them. If you're working on a vehicle, you got things like distributors and mechanical starters and points ignitions. We might happen to have an electronic ignition, but let's use points for this particular one so we stay mechanical. And we're going to have like ignition coils, right?
Yep.
We're going to store voltage and we're going to fire it off mechanically. We're not going to have a lot of control over it. Well, what about over on our air conditioning? I guess my hands are backwards. Let me over this way. Let's go over to the AC side. We're talking about a contactor that is driving motors, single speed operated motors with assistance of capacitors, right? We're talking about basic fundamental operation of a air conditioning or refrigeration system.
On or off?
On or off. It's a light switch. Either one, light switch, right?
That's right.
So let's think about what's changing to make sure we're comfortable with this transition. Because when we get comfortable with all the components that make up this transition, you'll be more comfortable with the transition. So here's where we are. This is where we're leaving. This is where the uncomfort zone is going to be. But we're going to break that. Week after week, we're going to break that uncomfort zone. And we're going to make you advanced technicians. All right?
That's right.
So here we go. Automotive started evolving. We had the automotive evolution. We went from our mechanical controlled systems into electronically controlled systems, and we added a processor. It's got a variety of names. CPU is a common one, central processing unit, or main board, computer, all sorts of things you will hear this board called. But what is it? It's a calculator, right?
Inputs, outputs.
It's inputs and outputs.
Garbage in, garbage out, right?
And that is exactly right. If I feed this thing garbage, it's going to put out garbage. If I feed it good ends, it's going to send out good ends.
That's right.
So when we talk about our inverter, all we're doing is we're using the exact same construction. We're using our calculator to be able to make our controls. So let's look at the components that make up our inputs and outputs for our processor in either one, just so you can be more comfortable with the analogy. Let's look at how these things are going to read temperatures. Right? So we're going to use some type of sensor, a thermistor, or we're going to use thermocouple. We're going to use something, typically it's thermistor, so that we have a nice variable
and
DC
accurate
voltage and accurate. So if we look at our processor, our CPU on a vehicle, we're going to use things like intake air temperature, our low side temperature. We're going to use things like exhaust gas temperature, our high side temperature. So we have inputs. And remember, what kind of voltage, Todd, is our vehicles already running on?
all direct current.
It's all DC, easy to modulate, right?
Yep.
So a lot of our sensors, we're just going to drop that voltage down. And what's funny about it is a lot of these thermistors on automotive are actually operating at 5 volts DC. All right. Depends on the manufacturer of the system, but there's a lot of them out there that are operating on a 5 volt DC platform. So we send in a positive 5 volt DC. We have a ground or a neutral. And then based on the temperature, we have a variable DC voltage coming back out as an input over to our CPU. So we have low side temperatures on a vehicle. We have high side temperatures on a vehicle. And we get over to our inverters. We've got
thermistors.
we're back again.
Yeah.
And most of these are actually going to operate on 5 volt
DC voltage.
Right? So it all comes down to converting it.
But wait a minute.
Yes.
How do we get to DC voltage?
You run. Let's hear it.
Well, this inverter is going to do a wave rectification from our alternating current and
incoming AC.
Incoming AC, sine wave, right? Mm-hmm. Whether it's 240, 120, whatever it's going to get. And it's going to convert it to a usable through a wave rectification of the inverter and turn it into a DC that we can use. And the beauty about DC is we don't have to worry too much about Ohm's law with adjusting the voltage. We can just adjust the voltage. I mean, you guys all have drill motors out there when you take cabinets off, right? What do you do with that trigger? You can vary the trigger a little bit, right? Well, does the motor burn up? No, because it's direct current.
Exactly. And when we put it into a 3-phase application, even better, like say our compressors, most of our compressors are going to be a 3-phase motor, and we're not even changing the voltage.
And we don't need a cap.
No, not needed. We're just taking our high voltage. And remember, it's about 130% of the incoming AC voltage on average. So if I've got 120 volts AC going to it, and I've got 120 volt AC mini split sitting right over here on the shelf that I use to tear apart for doing training purposes. So I got 120 volts in, and I've got like 150, 160 volts out for my DC. If I'm talking about a 240, 230, 240 volt power supply, I'm somewhere in that 300 volt DC output. Right. So then I got all kinds of current, right? I got all kinds of voltage. I got my pressure. My voltage is pressure, remember? So I got my pressure behind me. And if I want to fire a 3-phase motor, I just control the timing that I fire each of those 3 phases with a lot of nice power. Makes it nice and efficient, right?
Yep.
So now we've got our input in temperatures. So we can look at our low pressure temperatures or our low side temperatures, our high side temperatures. Now we can start throwing them everywhere. When I did grocery refrigeration, I did a lot of new grocery startup and commissioning, and I worked on some old ones too, but a lot of new stores. If there was something I wanted to monitor the temperature of, I just threw me out a thermistor and give it a location and went monitor this. And if I wanted to monitor 2 of them, I put 2 of them and I said, subtract this one from that one and give me what that number is.
The average.
Yeah, or average it. So all we're doing is we're just looking at different points so we can have precise calculations in our control. So let's take it a little step further, right? You ready? What about pressure? Anybody ever thought about pressure on a vehicle?
Sure.
A lot of people. I do. You do.
Fuel rail pressure.
Yeah, income map pressure, manifold absolute pressure, exhaust manifold pressure. There's a variety of things that we look at on a vehicle. So let's look at, say, the map, manifold absolute pressure. We're looking at the air coming into the engine. That's on the low side of the system. We could also look at the EGR, the exhaust gas side of it. We can look at the pressure on that side. And now we have a pressure calculation, same 5-volt DC, nothing crazy. Whatever the voltage is that it's using for the temperature thermistors, it's probably using the same voltage for the pressure transducers. What about boost pressure? Now we're going really positive. Instead of being negative on the low side, we're just going to be positive on that low side so that our output is multiplied. What pressure? What happens if I increase the pressure on the low side? I'm going to increase the pressure on the high side as well. I'm going to increase input. I'm going to increase output. So now we've taken some temperature measurements and we've taken some pressure measurements, and our processor has done some calculations on our controller. Well, what about our inverters?
Pressure transducers.
That's all what it is. It's another 5-volt DC pressure transducer so that we can read pressures on the low side and on the high side of the system.
And for those of you who don't know what a pressure transducer, say you didn't get there, a lot of us have with, guess what? We're getting away from true old school manifolds, exactly where I'm going with this. And we're using these right here in your hand. Your hose is nothing.
No, right? Absolutely. It's gone. Man,
and so that, it just turns into a Bluetooth signal and goes to your app. You measure quick, the Testo, Field Piece, whatever app.
Right, you have them out there.
And it spits out a known number that you guys are used to seeing on your analogs. In fact, all digital manifold gauges, even with hoses, are pressure transducers.
That is such a good analogy. So what are we doing, right? Let's grab the old handy dandy Testos. I had my Testos and I-manifolds floating around. So if I'm talking about wireless gauges, digital gauges of any kind, any brand, any model you want, you ever notice what kind of batteries we're using in these?
Usually AAA or AA's.
DC voltage batteries, yeah. So thermistor, we're sending a voltage. So we're using typically two AA's, 1.6 volts apiece, so about 3 volts. So we send a 3-volt positive DC supply to our temperature thermistor, and a variable DC comes back, and we send that variable signal back to our manifold, our calculator.
Or pressure.
Or phone, whatever we're using. Pressure transducer, exact same way. All I have is a pressure transducer operated by DC voltage. Whatever that variable DC voltage is, it comes back as a signal back to my processor. Well, what happens when we put those on the piece of equipment? And we leave them there.
Well, guess what? We do that all the time. They're on our high sides and low sides.
On a lot of equipment, people don't even realize. This is where it gets fun. This is why I love talking about this stuff. We can make this real. We can go, oh my gosh, is it really this simple? Yes, it is. So what are we going to do with our inputs on our CPU on a vehicle? We're just going to use it to control the capacity.
Yep.
We're going to control the pressure, the fuel going to our fuel injectors. We're going to control the voltage and the timing going to our ignition coil, which is now tied directly to our spark plug so we don't lose it in wiring.
Yep.
When we get over to our inverter, well, and we're just going to operate electronic expansion valves. Remember, DC voltages still. We're going to operate fan motors, sometimes with DC voltage, sometimes with 3-phase. So it just depends on, which style we use, depends on what the board wants to do. Depends on the horsepower of the motor that we're driving. as much as anything.
And also depends on the motor type too. If it's still an alternating current motor, then we got to turn it into we got to
then we have to rectify
frequency.
Exactly. And so there's some different exactly. But like our DC voltage, we can check all that on our board. Yeah. We've actually got DC test ports. I got to tear one apart and do some more inverter board training because they're simple to check them, right? It's just like checking a car battery. We can actually check the DC voltages on an inverter board. All right, so we got inputs, Todd, that goes to a processor that controls some outputs.
Yeah.
On a vehicle and on an inverter. All right, well, thank you all so much for joining us. Any last minute things in the chat? Looks like we pretty well got it all covered. A lot of good conversations today.
And if you need to get in touch with me, it's my name with right there, hvacredu.net. First name, TODD.
Absolutely. Everyone have a wonderful evening, and we will see you all next week on Did You Know?